So I am at the University of Michigan in Ann Arbor. Um, um, we are kind of close to Detroit, that you probably all know, but of course, also University of Michigan. I live almost literally at the automotive laboratory, where we have a lot of work for more than 100, nearly 100 years. Working in automotive together with automotive industry, and of course a lot of you know about manufacturing, but we're actually one of the important aspects is that we have a lot of technical centers, R&D centers around us, and so a lot of good, amazing students. Um, Along with all these nice things that we do, comes with responsibility. At the Automotive Lab, we recognize that transportation globally contributes something like 20% of the carbon dioxide and the global climate change. Um, and from that, 15% is passenger vehicles, at least in the United States, and 5% is commercial. And so you and I and everybody that drive cars, we are we need to pay attention. And at the automotive laboratory, as I've said, we were not exactly at the beginning of the internal combustion engine, but we have been working a lot with internal combustion engines, all these 125 years of internal combustion engine, uh, progression. And this is a really nice graph that was done a bit a while ago from one of my colleagues. Um, you can see at the beginning of internal combustion engine and the fuel economy in miles per gallon in a logarithmic sort of scale, increasing. There were some drops when we unfortunately couldn't deal both with emissions and fuel economy, but fuel economy was always in our mind. And fuel economy is important, right? Because it is the total cost of ownership, and it affects our paychecks and our bills, actually, I should say, not paychecks. Um, but at the same time, fuel economy aligns really well with CO2 and carbon dioxide and global warming. So if we improve fuel efficiency, we will actually, since these were fossil fuels, we will also reduce the impact to the environment from global warming. Um, but again, very important aspects associated with not just the environment, but also for economy. 2 trillion gallons fuel saved since the fuel efficiency standards were enacted. So hopefully they will not be misplaced right now, and we will continue the path. As you can see towards the end here, where we went back and forth between setting standards, pretty high standards. Many of us in the industry, especially after the Volkswagen cheating scandal, we realized that internal combustion engines, have reached a point where it's very hard to push further and further. So among those of us and many others, we realize that efficiency and prosperity does lie into our emphasis now on batteries. So we had a US goal, in fact, of 50% sales of light-duty vehicles, which, if you do the math, and it's not very difficult math, you can assume a 300 cells in a vehicle, the type of 300 cells that they are in a volt, or actually, sorry, a bolt, or the larger ones that they are in some of the Tesla models. And then you can calculate 10 million EVs per year that we need to reach the sales goal, and that would be 35 prismatic cells per second. That was and is still our manufacturing, to be honest, goal in the US, to still be able to produce these cells so that we can consume them also and put them in our cars and drive them. Um, And so as you can see in this picture, here is Michigan, right? There is a little bit of a belt going up south, north, all the way with Michigan, very high concentration of gigawatt hours a year, at least the ones that they were initiated. Unfortunately, a lot of them are right now stalled and in question. So I will use my trademark now slide that I think a lot of people know me about it. I say batteries are like humans. I realize this seminar is for mostly for controls people and computer science and ML and data scientists, and not really physicists and chemists. So hey, I'm trying to make it a little bit more concrete to you when I describe all this physics um, to relate and remember them. So batteries are like humans. They hate to be overworked. They don't like extreme temperatures, neither cold nor warm. They are very diverse in chemistry, size, and shape. As I always say, this is the only place in my life that I wish we had less diversity so that we can have more standardization. They're statistically faulty and they're all going to die. So the goal actually for every material that comes out of Earth is to be used as much as possible. I hope that is, a true goal for all of us. I mean, we like our shiny new things and we like to go shopping and do retail therapy, but at the end, everything needs to be used. And in the case of batteries, the more amp hours throughputs we put through a battery for 1 kilogram of whatever is that material, lithium, nickel, metal, cobalt, the more kilowatt hours, the more electrons pass through it, the better it is because then it's utilized, right? Utilization is kilowatt hours per divided by kilograms of the material. And so ideally, we want to use these batteries, and of course, we don't want them to end up in the landfill without harvesting the material. There's a lot of emphasis on the discarded batteries and recycling batteries and harvesting the material to put back in a new product. But in the case of batteries, they're actually pretty difficult and expensive to manufacture, not only to mine the material, but to also manufacture, to assemble, to package, to use. And therefore, the more we use them in its original shape and form, the better it is when it comes to energy and resources. And because, as I said, batteries are like human and they don't like temperature and pressure and all that stuff, and they're very sensitive, they have also a battery management system. So the battery management system, which is where the control engineers come in, a lot of times is basically we measure current and voltage. This is a graphic from Greg Plett and his nice book on battery management systems, the series of books. So we measure current and voltage and also a few points in a pack temperature. And then we estimate what we call state of charge. So this is, think of it as your fuel gauge. That tells you how much range you have left before you need to recharge. But it also tells you the state of health, which means how much capacity you have in the battery as the battery ages, like us, humans. We know we have an expiration date in a sense, which is what it means. It's like basically there's no quality of life at some point, right? We get sick, we can't manage anymore, and at the end, okay, we die. In a battery, it's similar, right? If they get aged and degraded, they will have all these problems associated to the fact that they don't, their capacity shrinks and they cannot go that far anymore, even at the full charge, and the resistance increases, and that's state of health estimation. Then we have many cells in a pack, and one of the big control problems is to actually, in fact, in some sense, the first control problem. All these things were estimation problems. And the control problems are these two. It's balance and equalize cells. Cells to cells have some variability. As they age, their variability increases. So there is a lot of effort to balance the cells and the charge so the strong cells can take more charge and they can kind of relieve the weak cells. if that's possible. And then another control problem is, we are like police. We do part denials. We need to make sense that when the battery, it's over temperature, overcharged, or reaches some limits, then we would actually stop and say, hey, you can't take more charge. You can't take that charge so fast. You have to cool down, all these type of things. So power limits, computing and applying them. Okay, so in order to do this BMS, okay, if there are any questions, by the way, for those on YouTube, I don't know where you're typing questions, but I'd love to see questions in the Q&A in the Zoom that I'm actually watching. And if I see questions, I can, yeah, I'll know you're watching out there. Okay, so for those of you who don't know the insides of the battery, since we're going to do battery management and they're sensitive, it's good to actually understand what's going on. So this is a sketch, admittedly, from my daughter when she was younger. And hey, I love that sketch. It's very simple. It says a battery has 5 layers. So we have the outer layer, which is the aluminum and the copper, and these are the layers that they carry the electrons. So we call them electron collectors, electron current collectors. And then on the copper and the aluminum, on each side, we have the active material. On the copper, we put the graphite, which is what we call the anode, and it is where the lithium is stored. So when the battery is fully charged, that's where the lithium will be, at that black layer that you see there. On the other side is the metal oxide, which is another layer that the lithium can go in and get stored when the battery is fully discharged. So the lithium just goes back and forth, and that's the magic. And actually, the other magic is the separator. As you can see, the middle layer is the layer that, in fact, allows only positive ions to go through and not negative, and that's why it forces the electrons to go around the circuit and we get the electricity. Boom, a battery. Okay, I forgot one more element. So 5 layers dipped. Think of it as being soaked in this electrolyte because the lithium travels through the separator and the material because of the electrolyte that allows actually that kind of like conductivity and diffusivity across all these layers. Okay, so here they are in realistic pictures. So we have these various layers. Then that I just showed you a single layer. So what we do is we make these long layers and then we roll them up like a toilet paper, very expensive one with 5 layers. And then we kind of take that roll and we squeeze it inside cylinders and we make cylindrical battery, or inside pouches and we make a pouch battery. The material, that active material that I was telling you, there are these blobs of this nice material. In one side is graphite, sort of like your pencil tip. And then the other one is the metal oxides, which is the very expensive stuff because it's metals. And so what happens is a battery, it basically takes lithium back and forth between these layers. So these layers are shown upper and lower here. I think you can see also my mouse, right? Give me thumbs up. Okay, good. I see. Okay, so this is what happens in its layer. So when we are charging, and this middle graph is what we measure. We measure actually the voltage or the potential in the cathode minus the anode, and that is the terminal voltage. So we actually measure the terminal voltage. We don't know what happens in its electrode. We only know the subtraction of them. And that is because when the battery is charging, it basically fills up with lithium, the anode. And so because the carbon that is there fills up with lithium, it becomes more and more like lithium, and its potential against lithium becomes zero. And then the cathode loses lithium, and so it becomes less and less like lithium, and so its potential increasing. The difference between this and this gives us the high voltage when it's fully charged and gives us the low voltage when it's discharged. Boom. Okay, so now you realize the big estimation problem. The estimation problem is we measure this voltage And by the voltage, in a sense, we know if a battery is fully charged or discharged, right? Because if it's high, it's charged. If it's low, it's not so charged. But what really happens is the real chemistry and the real physics are happening in these other two things that are kind of like obscured, and we only measure a composite. So this is an estimation issue. In fact, if we really want to understand what's happening underneath. Okay, I just said all these things, fine. I'm going to go really quickly for those of you that, don't know batteries, or for those of you that know batteries from the chemistry perspective, but here is the most simple estimation problem in the BMS is obviously to tell us when we need to plan our charging to make sure we don't run out of um, lithium, let's say, in our anodes to keep the car going. So the state of charge estimation is a very simple, to be honest, problem, but difficult. Simple doesn't mean that it's not difficult. It's simple to explain, but it's difficult. Let me show you the difficulty. First, let me show you the simplicity of the problem. State of charge is like an integrator. For those of you that you work with robots and cars and running around autonomous stuff, it's basically like, measuring velocity and trying to estimate position. Duh, right? For control engineers, it's like as plain as that. So indeed, state of charge, which is the Z, is this normalized capacity. So Z dot, the change in capacity, is the current I'm drawing. If I'm taking current, I'm dropping the capacity. So that's why it's minus. And then you normalize it with a capacity, like the maximum capacity of the amp hours that you can carry in your pack. That's the capacity. And this is just normalization factor going from amp hours to seconds, just nothing. Forget about it. So it's just an integrator. We apply current and we want to estimate the Z, right? That's all. So like a car, we measure, velocity, or maybe we measure acceleration if you deal with accelerometers and you want to estimate velocity. That's what it is. Okay. Well, you'll say, hey, if I have that, then actually I know that I will have, an integrator has drifts, and depending on my sensor of the input, I will end up with unknowns. Moreover, I don't know the initial condition of the Z, so really, I need to get some measurements to verify occasionally. So what is the measurement? Well, it's open circuit voltage. So open circuit voltage, which is this terminal voltage when the battery is not drawing current and it's kind of like calm, like after you took the current, you just wait, then you take voltage. This terminal voltage is just a function of Z. You can see Z here, Z there, Z everywhere. And it's just, we can express it with a lookup table or with a nice polynomial that captures this nonlinearity, et cetera, et cetera. Not big deal. You can do a fancy neural network. You can do whatever you like. Fine. So basically, then what we have is the terminal voltage is this terminal open circuit minus the IR drop. So it's the simplest battery model in the world. So given this model, I can write my estimator as always. So my estimator, I'm going to put hats, and then I'm writing the model, and then I have the output injection. This is the voltage that I'm measuring, unfortunately with noise, minus the estimated voltage. Then the estimated voltage is blah, 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 based on my model. This is the initial condition, unknown. And now I can run my error, and the estimation error in the Z is, you can see, exponentially decaying. So indeed, depending on my L, it's just an integrator stabilization. So I can basically stabilize my aerodynamics. This error gain, that can be fancy one, Kalman filter, it can be UKF, it can be whatever you like. Here I have a very simple gain. It will affect the noise, of course, so you cannot crank up that gain to converge your error to zero very fast. So unfortunately, it affects. So the error at steady state, it's going to be inversely proportional to the to that gain. So you want a high gain so that you have a small error. It depends on this alpha. This alpha, let's see what it is. Aha, it's here. So it's the slope of how the terminal voltage depends on state of charge. So the steeper is the slope, the better is your estimation because, right, you have sensitivity, like it's like observability. More observability, better it helps your estimation error. And then what these delta C and delta R are basically my model uncertainty. That's my modeling error, I guess I should say. Okay, what I'm highlighting here is that if for this particular chemistry of batteries, if I have a noise of a little bit noise like this gray bar, then unfortunately, because this alpha is so flat, so small, I can have an error as much as, 20% error in my state of charge estimation. And so that is a little bit of a problem. That the error can, of course, be affected by my modeling error in resistance and my modeling error in capacity. Aha! So now, okay, we breathe in, we breathe out. We say, okay, that's the problem. We know it's a classical problem, but now you can see that capacity and state of health estimation now affects your state of charge estimation. So it's a loopy thing, and we need to do joint state and parameter estimation now for the model. Okay, so how hard it is to compute and estimate state of health, and how does your capacity degrade? So that's what we call aging, right? So these are cycling levels, cycling conditions of the cell when it degrades and it lives its life. All cells must die, I said, all cells degrade and age. So what you see here on the left-hand side is capacity. Forget all these details. Just think of it as capacity. So as you use your cell and you put electrons through it, so that's amperes throughput. Think of it as miles or days. This axis, this x-axis, you can see that all my cells are reduced, their capacity gets reduced. The cells that they have a red color here were cycled under 45 degrees Celsius, which is high temperature for a fuel cell. It's warm. The blue are cold, nearly sub-freezing conditions, and the green that they last longer are the room temperature. Hey, I told you, batteries like room temperature, like humans. So this is basically shows you the range reduction over life. On the right-hand side, it also shows that the resistance increases, and that corresponds to a power fade. So if your lithium-ion battery is in a hybrid vehicle instead of an electric vehicle, that would affect your hybrid power capability, your heat losses, because this resistance creates Joule heating. And you can see again the temperature, high temperature loses or increases its resistance really fast. The immediate one was the cold condition. You can see what we call these elbows. It's because it looks like this, which is abrupt resistance degradation. And we call these the knees when we see uh, abrupt knee degradation. And these are important to be able to, let's say, forecast, predict when they're coming, depending on how you use the battery. So the reason for this degradation, oh, by the way, sorry for not telling you all this. The various lines within the color correspond to how fast you charge discharge. So the higher is the C rate, the fastest is your degradation. Also, the other kind of conditions we tested was if you have full depth of discharge or not. And so if you have full depth of discharge, that means if you charge fully, and let's say you have an Uber vehicle or you have a battery, lithium-ion battery on the grid, and it does every day a full charge discharge with solar and pushing back to the grid, it will, its life, it's going to be going faster in a sense than if you were to just have a smaller depth of discharge. And we have a lot of papers, and you can follow this QR code to get the data, because we have also the raw data associated for those of you. This is a nice data set because it's open and free, and also because it has knees and elbows. Not many data sets out there have this accelerated degradation phenomena. And I think it's interesting sometimes for those of you that you do machine learning and data-driven approaches to look at chemistries that they have knees and they don't have knees, because frankly, if you have a linear degradation, hey, I can do an extrapolation with a line. I don't even need ML. I don't need any learning. I can just easily extrapolate with a line. Uh, but if it has things like that, like knees, then hey, that's where I need you guys to do the fancy stuff. And
Yeah,
I'm not a
so,
data
sorry to
scientist.
interrupt you. There is a question from YouTube channel.
Yeah, go ahead.
So people are wondering, does the estimation incorporate the temperature effects? Because you mentioned about the cold weather, it may have affect the resistance.
Yes, yes, yes. So ideally, our estimation and prediction needs to account for this both increase in resistance, which is actually fairly large. You can see this is 100% increase. So if you look at this, this is 100% increase, and it happens at 2500 amp hours. By the way, this 2500 amp hours, I mean, it's still enough for driving the car for 10 years. It will have warranty. So it's a good car. It's a good cell in some sense, kind of. These cells were not that good, and in fact, because they were, they're very old generation. Things have evolved quite a bit, and we've improved them even further. But you can see that the work that I will show you, that it's physics based, physics driven. We do capture temperature in our physical um, mechanisms. I hope that helped answer the question.
Yeah, there is another
Eh,
question.
Okay.
It's for the slide 11. Could you clarify how do you make the SOC estimator robust to agent-induced parameter changes like delta C and delta R? And if so, how that influences the model complexity?
Yes, yes, that's right. Thank you. So this is my prelude. So the stuff I'll show you next is basically how we do state of health estimation, because you need to do both state and parameter estimation. Not in the same time frame. So the problem we have written, write to me, we have written a paper. I think I have somewhere the paper. Maybe I don't have it here actually. We have a paper here that quantifies, has error bounds with respect to the unknown parameters, capacity and resistance. So you know how much it affects. But also we have a paper that does the joint estimation, parameter estimation, and it shows how you would do it and what the problems are, in fact. So for those who are asking, please email me. I can send you the paper. It is with Yonki Kim and Sankar Mohan, probably 10 years ago, 2014. Okay, so if you do Google and you're working through recent papers, you won't find it. You have to go to 2014, 2015 era. I think so, yeah. Okay, yeah. So we obviously we understood that data-driven capacity estimation is, of course, what people are trying to do. But to be honest, we don't have too much data to be able to do it. We have, to be honest, we are in the beginning of this electric vehicle. Like we don't have so many aids packs and cells. And even if we do it in the laboratory, the issue is that we can train something, but how do you train in a global way? So what we're trying to do in my lab is what we call the hybrid approach, which it embeds a model, physics, and then we use the data to parameterize the model. So as this picture shows, is you have capacity loss and power fade. For different reasons. So what we have now is all these causes that we know that cause degradation of capacity, and this is the output that we want to estimate so that can help us understand the state of health. And this is exactly the question here. How do we do state of health estimation for capacity. So I want to show you, before I dive into the sort of, the estimation problem, why capacity estimation is very hard to do. And I will show it to you first, not in the field, but in the laboratory. It's even hard in the laboratory. I want to show you in a laboratory, very controlled case, and show you the difficulty so you can extrapolate how it is in the field. So these are my guys. They're running a lot of cells. So I'm showing you a picture of a cell that charges, discharges, charges, discharges, goes back and forth in 10 to the fifth seconds. That's something like 3 months. And this way we age it, right? We basically run it back and forth every day, actually multiple times a day. And this is the measurement we get, voltage. Again, remember, in a car or in a battery, the only thing you measure is voltage right now. Okay, so you look at the voltage when it's fresh, and it shows, so this is, sorry, time, hours, this axis, and it shows that the voltage when it starts as empty, then it goes up, and then you can charge for 4 hours, 4.5 hours. So this is because it's 10 amps here. Sorry, this is amp hours, so that's 5 amp hours, 4.5 amp hours. When it ages and you look at the voltage trajectory here, you see that basically when you start with minimum voltage, you will hit the maximum voltage much earlier in less time. So you see that the capacity now has shrunk to 3.5 hours. So this is how we measure in the lab the aging, the capacity, by looking at the voltage, seeing how much, let's say, time or coulombs we put through before you hit certain voltage range, and that's what tells us capacity. Now, the problem that I want you to see here is that if you had a car that you charge all the time, so you're up here always in the measurements of your voltage, and you do a very small trip home and back charging and home and back charging, and you never go down here, you will never see a difference between the blue and the red line. So sometimes the voltage, the high voltage measurements are not capable of telling us degradation. You have to actually go to beyond 50% depth of discharge, like, more than 50% empty your pack when the voltages start really deviating and you start having a good signal so you can do good estimation. Right? And you see it clearly in this graph. I didn't even need to go to the field to tell you that now the car is driving and it has a non-constant current. This was under constant current condition. So very simple experiment, right? So why is this happening? Again, this is happening, this unobservability aspect. I wrote it back in 2010. So that's now 15 years ago, guys. And we had this issue about being able to understand through terminal voltage our ability to estimate what happens in how fast the metal oxide, the cathode empties, and how the anode fills up, because that's what determines the capacity. And what you see here is when the anode degrades, which is this here, you can see that maybe in the beginning it was like all this capacity, and as it degraded, it scales, it shrinks, and it also shifts, but you only measure the output, this minus that. And so what we got to do is try to understand the observability problem and the estimation of both electrodes, and under what depth of discharge you get full observability. So you can set up the problem with the voltage being as a function of these stoichiometries, and the stoichiometries can be defined as a function of unknown parameters, and then the capacity, the amp hours throughput, which is this Q, and then you take your terminal voltage measurements, and then you can do all these nice, calculations on the error bound. You can see this is 2020, 5 years ago, where we saw clearly that when you have a shallow depth of discharge, your errors on anode and cathode can be as much as 30% in some chemistries, so really high. But when you do deep depth of discharge, then you actually get very good errors that also allow you to do good estimation for your range, obviously. What I'm showing you is not a sort of a, kind of a weird thing that I did just to show you that estimation is difficult. It actually happens in many chemistries. Why? Because every battery, has this soup of acronyms that probably you hear about. They are the cathode, and the cathode can change, but most batteries use graphite and silicon right now, conventional batteries. So all of them, they have this flat voltage. And because of this flatness of the voltage, there's no observability of how the graphite ages up until you actually almost discharge it. You're at this range or this range. Okay. Okay. But I want to show you something also interesting that we do also in my lab, and we are unique in that when we age our cells, these are pouch cells. When they are pouch or prismatic cells, we can put them inside these fixtures and not only measure the voltage, the terminal voltage by taking current like it shows here, we can also apply pressure to them and measure their expansion. And you say, expansion? What? You mean my pack will expand? It actually does. And you put foam in between cells to absorb this expansion. So what you see here is that as the cell are fresh, they actually what we call breathe. They have this reversible expansion. So when it charges, it swells. It's like filling with your lungs the oxygen with your lungs. So you breathe, you charge, you discharge. Okay, it makes sense, right? It's material. So the lithium goes upstream, it kind of swells and intercalates and it opens up. At the end, you get to see the measurement in dimensions outside the cell. You don't need to get, complicated sensing. So the issue also is like as you age, this swelling of your lungs, well, actually of the diatomic structure also shrinks. Like as we age, we can't run that fast, right? Why? Because our lung capacity goes down. So now this reversible shrinks, and you see it here as it ages, and it also increases irreversibly. So the cell swells because of all this material breaking and all this processes that are happening and they're building up inside that they make it irreversibly age. And that's also what I call, so here you can see that as the cell again charges, the anode expands because the graphite and the silicon expand. The cathode, the material, the cathode decreases. And the combined measurement is what we measure, the thickness of the cell. And as you can see, this is the thickness we measure. It's actually much, let's say, clear signal to noise ratio than the voltage that was very, very flat. And so that allows us to actually do very good estimation if we can get measurements of expansion. And I will increase now, my batteries are like human by saying cells breathe, they expand and contract. And also we end up gaining weight and waistline as we age. I always buy bigger size pants whenever I buy them, and that's kind of scary. And there are some nice explanations about why. Now I'm going to tell you so this is the diatomic structure as the lithium intercalates, how it expands. And this is when you build up material and then eventually you build up the thickness that we measure. We have built a lot of sensors that we can use in the field that you put in packs. So when packs are assembled, cells are assembled in a pack or a module, they typically have foam or braces in between so that they can either absorb the swelling or contain the swelling. So they're under pressure and compression. So instead of measuring expansion, we can also measure the load, the pressure that they exert. And by this measurement, it's an additional measurement. It can improve our stability. And I'm a little bit behind, so I want to brag about the fact that we, in the beginning when we started doing all these experiments and getting to create this additional measurement signal, we were paying $2,000 per sensor for every cell. And that's because these are microns. So don't think of it as swelling hugely, right? Microns. Um, and it's over life. So these microns should not drift and should not, be noisy and all that good stuff. So very expensive sensors. So we actually did a principle with frequency and inductive motor where you can measure the frequency as the cell swells, and that changes the space here, and so it changes the frequency of the induction. Okay, so that was ARPA-E project, and we got a big award in the Control System Society for doing all that sensing, augmentation, and good observability. So having now these sensors, or maybe without having these sensors, what I showed you just with voltage alone, I showed you that instead of just looking at capacity and resistance, we can advance actually our state of estimation to actually do state of health for each electrode, which is what we call electrode-specific state of health estimation. So we know what the anode and the cathode is doing, and the electrolyte is draining, and that allows resistance increase. So we are now at this spot where we say, okay, so we are improving the state of health estimation. I'm not giving you the details on the algorithms, because that's kind of bog us down. I want to give you kind of an overview here of the field overall. So I want to tell you the kind of next challenges and transition to remaining useful life, because that's the forecasting and the prediction. So if you, let's say, are keeping good estimation of your state of health, capacity, resistance, can you forecast how long it's going to last given the current utilization structure? And the point I want to show you here is this big debate that is happening in the field. The European Battery Passport, it's a legislation that tells manufacturers and battery pack manufacturers to make sure that they do have state of health estimation, and their state of health lasts for 8 years, let's say 100,000 miles or 160,000 kilometers, and it's not below 70%. And what this graph shows is 3 different packs, pack A, B, and C. Since all these manufacturers are going to sell their packs, that means they have to qualify that they will maintain state of health and satisfy the battery passport and the California Resource Board, what we call durability for packs. Which they require a dashboard indicator. So when you buy now electric vehicle, well, not now, I don't know if this legislation is going to continue, but the plan was to actually, in your dashboard, you have range, right? Tells you how many more miles the estimation scheme from state of charge tells you still have. You should have also an indicator of state of health. So it tells you how your battery ages. But our point was, as controls people, is that one point in the dashboard is not enough to tell you the remaining useful life. Why? Because you can see that all these packs satisfy the durability, so they can show you that, at 8 years, the state of health is 70%, so it's good. You don't recall or get warranty replacement and things like that. But it doesn't tell you that this pack actually had pretty slow degradation, but now it already hit the accelerated degradation, right? To do predictions, you need history. One point is not enough. In fact, because it's nonlinear, 2 points, you have the top and you have this, is not enough to tell you how it's going to go. You need some intermediate points, and therefore your state of health estimation indeed could be data driven, because if it follows this trajectory, maybe it knows better. So for this case, it is very important to have the estimation and also to have forecasting that can be also data driven or physics based like we do. And you'll say, Professor, why do you need physics based? This I can do a Gaussian process regression part of, something like that. And I can tell you both forecasting and uncertainty for each one of them. The truth is, yes, you can. The problem is that things some cells don't go straight like that. They're just like flat and then just like actually hit the knee. So for the knee and the nonlinear degradation, you need some physics, because it's not easy to forecast this nonlinear behavior. So that's what I want to say. One state of health value is not enough. Trend in SOH is needed at somewhere at midlife. So we are actually working with the policymakers to understand, how often, maybe how to ask users to do a deep depth of discharge so that they get assured estimation and put that in their algorithms to get better use. Moreover, if you have remaining useful life and you want to buy the vehicle here as a second-hand vehicle, the prior trajectory does not tell you how the new use case is going to degrade your vehicle. So it shows here that if as a second-hand vehicle, you start using it more often, you drive on the highway, or you go from a hot climate to a cold climate, then this degradation pattern can change. And unfortunately, forecasting with data-driven extrapolation is not going to help you, because you need inner mechanisms. And that's what I have here, that you need a deep degradation mechanism estimation for remaining useful life. Some of these degradation mechanisms have internal loops, and they're very nonlinear, and they actually have positive loops. That's why sometimes you have this accelerated degradation, because you have this unstable, in a sense, degradation. And instead of just doing this and this, we really want to do this. And that was the title in my slide that I said degradation mechanism, state of health estimation. And the degradation mechanisms are these here. And since I am running out of time and I want you to ask me questions, I want to point to the fact that these mechanisms are very nonlinear, very interacting, and even parameterizing them is very hard, right? So with physics, the good news here is that you need only one slide to write them. So they're not that complex, to be honest. I know it's a big slide full of equations, but hey, I mean, it's still one slide. And what I'm showing you here is the green parameters that we need to parameterize. So 1, 2 here. And if you have more complex degradation mechanisms, so we go up to 5 parameters. So if you get data from the lab, you can, pre-compute. I'm going to kind of jump ahead and tell you my vision here, in a sense that it's here, I guess, and say, that what we are thinking is to calibrate in the lab the model, and we have done it for several chemistries. And then once you have a model that is calibrated with some degradation patterns, then you can take minimum data from the field and then do your estimation with uncertainty with data-driven approaches. So it's again a little bit of a hybrid. I want to say that understanding degradation is also important in the first life, not just for the second life and resale value, because you can do V2G. You can decide if your car will hit the warranty in time before it reaches the miles. So, right? So what you want is to use your pack. You paid so much, right? If you go and you buy a vehicle 30% of its price or more, it's the pack. So why not using it, especially if they're paying you to help the grid? Well, to do it, you have to, I know you guys are data-driven people, so I'm gonna pull your leg here and say that data-driven confusion, data-driven approaches cause a lot of confusion in V2G. They're the ones that say, um, your pack will degrade, and they're the ones that they say, no, your pack, oh my goodness, what did I do? I know what I did. Sorry. Will not degrade, and it's kind of funny to say that it's very complicated. And again, what I'm saying is that you need to have some physics. What I'm saying here in this graph is that we actually do the state of health estimation and understand if you're maybe the first and the second year you don't do V2G and you establish a pattern. And then with your state of health estimation, you know if your degradation is SCI dominant, calendar aging dominant, or cycling dominant. That can tell you if you can do V2G or not. Okay, and it depends on the chemistry, but it also depends on how you use, where you drive, if you're in a hot Phoenix or in cold Michigan, things like that. So I'm going to say that also we have a lot of work ahead of us on understanding and doing fault detection for going from normal to degraded that I showed you so far, but also abusive and safety conditions, and continue with my batteries are like human chart and say when batteries are angry, they need to vent. So when batteries go abnormal, the first thing you see is they swell. They have gas evolution, and because they swell, part of their safety is to actually vent this gas. When it vents, it actually cools down and its resistance increases, so it isolates the cell from the other cells. So it's actually part of the degradation or of the safety mechanism. But unfortunately, these gases also create a combustible mixture in the atmosphere and potential explosion. So the idea is that you actually also want to estimate venting. And we have a lot of work that we've done recently on predicting this type of patterns. And we do experiments with a lot of venting and abuse to actually see the gas venting, and both with sensors and also, again, that expansion force. And the final effort we have is to actually improve the estimation during birth and manufacturing. And that's because if in manufacturing we do good estimation and we have the initial conditions of our states, then it would be easier to actually keep track of our estimation over life. I'm going to stop there and say all these things apply to all batteries. And although I started with automotive, we work with everybody all the way from, microelectronics to buses and battery energy storage and robots and stuff. And thanks a lot for inviting me.
Yeah, thank you, Professor. It's a really interesting and great talk. And we have several questions. The first one, Andreas has another question. Andreas also says thank you for taking the time to deliver such an interesting talk. And he's wondering whether the machine learning could be an enabling tool for better SOC estimation.
Whether the what? Say it
Whether
again.
the machine learning can be a tool useful for SOC estimation, be a better tool.
You don't need SOC estimation is as I showed you simple. Why would you use machine learning? I don't know. I would do machine learning in things that you know it's like back 20 years ago we had oh yeah, I'm not gonna bring it up. I was going to say fuzzy logic. If you don't know the physics and you don't have a simple model that can help you do classical control or, you know, uh, principled, then I'm not sure what machine learning will tell you for state of charge. State of health, maybe, because as I said, state of health is a complicated model that maybe you cannot parameterize.
We have another question.
Yeah.
It's about is the ability to recycle the cells also being considered as a part of the attempt to elongate the life of the battery?
Absolutely. I mean, at the end, we need to recycle. But the important part is to use the pack as much as possible and as long as possible. Not long by long. I mean, you know, in fact, if I show you a graph, I mean, the battery chemistry evolves really rapidly. This is from when it was invented to our goals we have now and in the future in 5 and 10 years. So batteries are evolving. In the battery energy density domain, things have started plateauing. So actually now a lot of um, improvements are going to be because of us, because of the computer control scientists that we do better and better BMS and integration of the existing batteries because we kind of started maxing out on the performance. So going back to the question, I guess is, well, so I think there is a lot of opportunity in being able to apply data-driven approaches and learning in state of health because our models are evolving to keep track with how chemistries and different, technologies are evolving. Unfortunately, I see the data being behind that curve, right? Because to get a data-driven approach, you need data. You need all this to be in the field and somehow to achieve the data mining for that. So I think I see me working closely with the data-driven people, people like me that I do model-based to kind of like fill the gap and have a combination of synthetic data and real data to improve the machine learning approach.
There's another question. Uh, could you comment on how physical based model compare with data-driven models? In typical applications, which approach tends to achieve the higher estimation accuracy?
Oh, it depends on the data and the training and testing. I can tell you now, right, with my models, I can have better estimation through, you know, two or 5 cells training and then 5 cells testing, even under testing under conditions I did not train, like no extrapolation, like really, sorry, no interpolation, extrapolation. I can do extrapolation with my physics-based model. And that's the part that I can do that I don't think the data-driven approaches can do. At the end, data-driven approaches could be more accurate in interpolating because, are, uh, they're more flexible. My model has a structure. So it's harder to parameterize, perhaps, but I need less data to parameterize. So that's the good thing. So I guess there are pros and cons, and so it depends. If you have a lot of data and you want to uh, precisely answer a very, very narrow question, specific question, you can do the training. I don't think you need the model.
I have one question just for the personal curiosity. You have a work about battery passport, which can give the guidance for the resale of the car. I just wondering, I saw like you categorize like the driving also behavior if they are like you abuse a battery or just normal or taxi. I just wondering like for the personal, can we also have some like heterogeneity, like more detailed driver style into this passport accounting, like adding more features.
Yes, yes. So let me see if I have it here. Yeah, so if again, how to say, it is possible, allowed, and if you allow it as a user, then the state of health estimation can be actually be tracked, and you can have an app in your phone that actually shows that trajectory for you. There is a company out there that does it and sells the app and and then they collect the data and they do data mining. They are, and I don't get funded by them, and I'm not, in their board or anything, so I can tell that they're doing fantastic job in that. But I can show you in this little graph that I have here. So this is what I call the throughput versus days ratio for V2G. And this is three different chemistries. And the stars are for different driving patterns. So the driving patterns, if you drive too much or less, or you charge late or early, you can modify your degradation pattern, but not much. The most important part is your chemistry. Okay, I hope I answered, but yes, it is
Yes, thank
possible
you,
now.
Professor. Thank you for the talk. Just one last question. Just some audience, they're wondering, are you gonna hire the PhD students this year?
Yeah, yeah. Funding was a little bit rough and a high uncertainty this last year. A lot of our funding didn't come through. So I think, yeah, if you're interested, please apply and reach out. And we always need good students.
Okay, thank you so much, Professor. That's all the questions we have, and we also finish our seminar. Thank you so much.
Thank you.